Hello and welcome. In this video, we will start a chapter on complex numbers. Now, in the chapter on set theory, we have seen set of numbers like set of natural numbers, set of integers, set of rational numbers. All these were set of real numbers. We have also seen that a real number is represented in a number line. A real number is represented on a number line. But there are some numbers which cannot be represented on a number line. What are those numbers? Those numbers are complex numbers. So we are now going to learn what are complex numbers. Now we know that a quadratic equation is ax square plus bx plus c equals to 0, and we also know that for the solution of this quadratic equation to be real, b square minus 4ac has to be greater than or equal to 0. For the solution of this quadratic equation to be real, b square minus 4ac has to be greater than or equal to 0. This means that when b square minus 4ac is less than 0, x is not real. This means that when b square minus 4ac is less than 0, x is not real. Now the question arises, then what is it? More specifically, if we have the quadratic equation as x square plus 1 equal to 0, we find that the solution of this quadratic equation is x is equal to square root of minus 1. So we are stuck at this position. We are stuck at this position because there is no real number whose square is minus 1. There is no real number whose square is minus 1. So this square root of minus 1 is given a special symbol, that is symbol I stand for imaginary number. This I is the unity of imaginary number. Suddenly there are whole new set of numbers called imaginary numbers. So an imaginary number will be a multiple of I, such that I, 2I, 0.3I, minus 1.2 bar I, EI, etc. If we combine real and imaginary numbers, we get a new class of numbers called complex numbers. So a complex number is a combination of real number and imaginary number. Now the next question is how to write a complex number. A complex number is written as z equals to a plus ib. A complex number z is written as a plus ib. The number a is the real component of the complex number written as Re of z. The number b, which is the coefficient of I, is the imaginary component of complex number written as Im of z. The numbers a and b themselves are real numbers, and I is equal to square root of minus 1. A complex number is represented in a 2D plane, the horizontal axis of which is the real axis, and the imaginary axis, the vertical axis is the imaginary axis. The vertical axis is the imaginary axis. For example, if you want to locate the complex number 1 plus 4i in the complex plane, we do it like this. We see that its real component is 1, therefore on the real axis it is located here, and the imaginary component is 4, therefore on the imaginary axis is located here. And if we draw lines from these two locations, we draw the horizontal vertical lines, it meets here, therefore the complex number is located here in this 2D plane. Similarly, the complex number 3 plus 2i is located here in the complex plane. Its projection on the real axis is at 3, and its projection on the imaginary axis is at 2. The distance of these complex numbers from the origin, the distance of this complex number from the origin is the modulus of the complex number. Therefore, the modulus of the complex number, which is written as this, is equal to square root of a square plus b square. This 2D plane, this 2D plane where the complex numbers are located is called the complex plane or the Argand plane. Please note that a real number is a subset of complex numbers. Real numbers are a subset of complex numbers because any real number x can be written as x plus 0i. Any real numbers can be written as x plus 0i. Therefore, a real number has imaginary component which is equal to 0. Now, how to check the equality of complex numbers? Suppose that we have complex numbers z1 equal to a plus ib and z2 equals to c plus id. Then z1 is equal to z2 if the real components are equal. That means the real component a and c are equal, and the imaginary components b and d are also equal. Therefore, z1 is equal to z2 if a is equal to c and b is equal to d. Thus, two complex numbers are equal if corresponding real and imaginary parts are also equal. For example, if we have two complex numbers 2x plus 2 plus y plus 2i and 1 minus 3i, and these are equals. So if the complex number 2x minus 2 plus y minus 2i is equal to 1 minus 3i, we are required to find the value of x and y. So we equate the real components and the imaginary components. So we equate the real components and the imaginary components, and we get 2x minus 2 equals to 1. If we equate real components, we get 2x minus 2 equals to 1. This means x is equal to 3 by 2. So by equating the real components, we get x equal to 3 by 2. Similarly, if we equate the imaginary components, we get y minus 2 equals to minus 3, and then y is equal to minus 1. Therefore, by equating imaginary components, we get y equals to minus 1. Now we move to today's last topic, that is the complex conjugate. For every complex number z equals to a plus ib, there exists a complex conjugate z bar such that z bar equals to a minus ib. So if a complex number is a plus ib, its complex conjugate is a minus ib. In the complex plane, if the complex number is located here, its complex conjugate is located here, which is the mirrored value of complex number across the real axis. The complex conjugate is the mirrored complex number across the real axis. It is interesting to note that the product of complex number and its complex conjugate is the square of the modulus of complex number. The proof of this equation, we will see in a later video. To summarize, in this video, we have learned the definition of complex numbers, we have learned how to check the equality of two complex numbers, and we have learned about the complex conjugate. In the next video, we will learn the algebra of complex numbers.